Before examining state space design techniques, we will look at modeling in state space, or in the time domain, using the state space representation. This video will go over steps for modeling or creating what's called the state space representation. There are two examples of this process. Then rules are given for choosing the state variables, and one example is provided at the end of the video. The two examples in this video will cover these 5 steps for modeling the system. First, we're going to select a particular subset of the system variables, and this subset constitutes the state variables. Then, once we have, in our examples, the equations of motion, for an nth order system, we will rewrite this as n first order differential equations. For an nth order system, we require n state variables, and this system of equations is called, or these equations are the state equations. On one of the examples, we will go ahead and solve for the state variables given the initial conditions and the input. If we're just looking at modeling, that doesn't necessarily involve solving the differential equations. But for a state space representation, we do algebraically combine the state variables with the input to find the other system variables. And these equations giving the other system variables are known as the output equations. Once we've done this and we have the state and output equations, we get what's called the state space representation. Our first example is a massless spring and damper system, shown here. So we have a force being applied to a massless plate that's connected to ground with a spring and a damper. So let's write the equation of motion for this system. We have that the damper times the velocity plus spring constant times the displacement is equal to the force. So this is a first order system. And therefore we just need one differential equation. And we already have our one different first order differential equation. We just need to rearrange it. Our state variable is position x. So we need to write a first order differential equation for our state variable. So x dot is equal to negative k over d times x plus 1 over d times f. Now that we have the state equation, we'll go ahead and, for this example, solve that to get the state variable as a function of time in order to see how we can get the system variables as functions of time. So we'll solve using the Laplace transform. And taking the Laplace transform of this equation, we have d times s x minus the initial conditions x is 0 plus k times x is equal to the Laplace transform of the force F. And for the step input, we have that F is equal to 1 over s. So now we can rearrange and take the inverse Laplace transform. So solving for x, we get that it is over s plus d times the initial condition. And now let's rearrange this in the form that we can use the Laplace transform tables for. And we will apply partial fraction expansion to the first quotient to get this expression for x, Laplace transform of x. And now, if we take the inverse Laplace transform of x, that'll give us x of t, and this ends up being one over k times 1 minus exponential k over d times t plus the initial value for the position times that same exponential. Now that we have the position, our state variable, as a function of time, we can algebraically combine this with our input to get other system variables. So back to this list, we chose the state variables, wrote a first order differential equation for this system, and then we solved for the state variable. And now we're going to write the output equations. So for example, we could combine the state variable with the input to get the spring force. So the force from the spring is just k times x. Or we could solve for the force from the damper, F times t. And now we want to get this in terms of the state variables and the input. So we have negative k times x plus f. And we could also solve for the velocity. And we want to get that in terms of the state variables and the input. So we have negative 1 over d times kx plus 1 over d times f. And this is the state space representation. We have a first order differential equation for our state variable, and then we have output variables or other system variables as linear combinations of the state variable and the input. So we have our state equation and some output equations, and that makes up the state space representation for this first order system. Our second equation is a spring mass damper system, and that's shown in this figure. We have a mass that is on, we'll assume, frictionless rollers, and there's a spring and a damper connecting that mass to ground, and there's a force being applied to the mass. So our equation of motion is given here, mx double dot plus dx dot plus kx is equal to f, and this is a second order equation. So this means that we're going to need two first order differential equations and two state variables. Okay, our state variables are going to be x and its derivative v. And our two first order differential equations, we need first order diff EQs for these state variables. So first one is x, so we have x dot, and this is a simple equation, it's equal to v. So we have differential equations for the state variables in terms of as linear combinations of the state variables themselves. So here's the first one, x dot equals v, and the second one, v dot. We rearrange this equation to get that. So we have negative k over m times x minus d over m times x dot, which is v, so times v, plus 1 over m times the input f. So these are our state equations. And now let's say output is going to be the force from the spring and the force from the damper. So we have, again, the spring force is just K times our state variable x, and the force from the damper, we now have the velocity as one of the state variables, so d times v. And these are our output equations. Now we're going to be working with the matrix form of the state space representation. Let me pause while I write. We want to come up with the state space representation in matrix form. So our state equation looks like x bar dot is equal to the matrix A times x bar plus B times the input u. So this is the state equations. And the output equation, y bar is equal to c x bar plus d times u, output equation. So what does that look like for this example? Our state vector, x bar is a convention for a state vector, so it could be confusing with the displacement variable that we had here, x. We can be sure to call this x bar. Bar represents a vector, so that'll keep straight whether it's the state vector or a state variable called x. So anyway, x bar is equal to the vector x and v. So our state equation gives us x bar dot, which is x dot v dot, and we're just rewriting our state equations up here in matrix form. So matrix A, so for the first equation we have 0 and 1 are our coefficients. And there's no input for that equation, so 0 for B matrix. And for our example, we just have a one input, so u is a scalar, and the input is force. Now on to the second equation. We have v dot, so we just take the coefficients here. We have negative k over m and negative d over m. And then for the B matrix, 1 over m. So here's our state equation in matrix form. And now our output, let's see, y bar is equal to a vector comprising the spring force and the force on the damper, Fd. And again, it's a linear combination of the state variables and the input. So for the first equation we have k and 0, and the second we have 0 and d. So we multiply that by the state vector and you end up with the output equations. So here is our state space representation for the spring mass damper system, where our outputs are the spring force and the force on the damper. Let me take a second to go over some rules or guidelines for creating the state space representation, specifically the state vector. You need to choose that subset of system variables that's going to make up the set of state variables, or the state vector. And one approach is to start with the differential equations governing the system. So look at those equations and define a state variable for each of the variables that have their time derivative in the differential equations. If you think back to the first example, the first order system, we had x and x dot, and so the variables that have their time derivative in the differential equations, x was the variable that had its time derivative. So x was our state variable. In the second example, where we had the second order system, we had x, x dot, and x double dot. So we had two state variables. X had its time derivative in the differential equations, and x dot had its time derivative in the differential equations. In other words, there was x dot and x double dot in those equations. So x and x dot were our state variables. And the goal of doing that is to transform however many nth order differential equations into n first order differential equations. So we had one set of nth order differential one nth order differential equation in our second order system. So we ended up with two first order differential equations. Now, for each nth order differential equation, we're going to have n state variables. And again, thinking back to the second order example, we had more than one state variable from just one differential equation. So for that second order system, we came up with two state variables. And one thing that bears consideration is that the state variables must be linearly independent. For example, this is not a valid state vector if one could say that x3 is this linear combination of x1 and x2, because all three of these variables are not linearly independent. The final example for this presentation is this rotational mechanical system with gears. We have two gear pairs, so three shafts, a spring. Each gear pair has friction, and there are moments of inertia associated with each shaft. So we want to write the state space representation for this system with theta 3 being the output. So we have theta 1, theta 2, and we'll say theta 3 is the displacement of this shaft. Since there is only one independent motion, that is, if you hold theta 3 fixed, then neither of the other two shafts can turn. So if you hold any one of them fixed, then the other two can't turn. So there's only one independent motion. That means that we're just going to have one differential equation. So that takes the form of this equivalent system. We have our torque going into the shaft, and that shaft turns an equivalent moment of inertia, and it's attached to ground with an equivalent stiffness and an equivalent damper. It's a pretty messy drawing, so here's a little cleaner version of it. KE, DE, and JE. Now from the original figure, we have that the moment of inertia seen by this shaft is this moment of inertia plus this reflected moment of inertia plus this reflected moment of inertia. We have that here, so we have 2 plus 4 over 12 squared times 1. So 4 over 12 squared times 1 plus this product squared. This is 4 over 16. 4 over 12 times 4 over 16 squared times 16. And that gives us an effective moment of inertia of 2.222. And now we can do the same thing for reflecting the stiffness. This is the only spring in the system, so it's reflected through both gear pairs. This product squared times 64 gives us an effective stiffness of 0.444444. And then for damping, we have damping on this shaft, D1, then we'll reflect D2, and then we'll reflect D3. So D1 plus D2 reflected plus D3 reflected gives us 1.444. And now we just write the equation of motion for this system. And that's given by this. So Newton's second law applied to this rotational system, tau minus ke times theta 1 minus de times theta 1 dot is equal to je times theta 1 double dot. And we can use this equation to come up with our state variables. So we have a second order differential equation that indicates that we'll have two state variables. And we'll choose the variables that have their time derivatives in this equation. So theta 1 has its time derivative, so theta 1 is going to be one of our state variables. And theta 1 dot has its time derivative, so theta 1 dot will be one of our state variables. I just rearranged that equation of motion, but the state vector is made up of theta 1 and theta 1 dot, which we'll call omega 1. Now our state equation, we have time derivative of the state vector is equal to theta 1 dot omega 1 dot, and theta 1 dot is equal to omega 1 dot. I'm sorry, theta 1 dot is equal to omega 1. And omega 1 dot, we have this equation for it. So negative ke over je, negative de over je, and then we have some input in that equation. 1 over je. That's multiplied by tau. And for output, we use the gear ratio, and that tells us that theta 3, so this is our output, is equal to the gear ratio times theta 1. Or really it's theta 1 divided by the gear ratio. Theta 1 times the inverse of the gear ratio. Okay. So here we have the state space representation for that system. We've got the state equation and the output equation. Now we've seen a little bit about modeling in the time domain using state space representation. Using the differential equation governing the system to determine the state variables, and changing that nth order differential equation to n first order differential equations to make up the state equation. And we've seen that the output can be described by a linear combination of the state variables and the input.